Hi everyone, welcome back to the channel, and in today's video I'm going to discuss one of the projects that I did when I visited Berlin this year. That's called Discounted Pseudocost in MILP. We'll start with the acknowledgements. So I couldn't have done this project without the help of Skip developers team, and specifically I would want to thank all these people. So these people basically helped me with the code of Skip and or benchmarks and basically evaluating the performances. So thanks everyone. Now let's get to the presentation. Without further ado, let's start with the overview. So I'm going to first talk a little bit about RL basics, reinforcement learning basics. Then we'll also discuss previous work in reinforcement learning for MIP. Specifically, we'll only focus on branching. Then we'll talk about the main idea of my project, followed by the evaluation, how it performs on the benchmarks. And finally, we'll discuss some future work, like how to extend this idea and what all things can be done to get even better results than what we have today. Okay, so let's start with the reinforcement learning basics. We have environment and we have an agent. So the agent operates in the environment. At a given stage, environment has some state information and that is known to the agent. At every step, the agent has a bunch of possible actions to choose from, and the agent will basically pick one of the action from those possible actions, and once the agent acts, then the environment is changed, so it will be in a different state, and this loop basically continues. Okay, what happens is that after every step, environment also gives some reward to this agent, and so that's called, let's call it RT. Okay, so the goal for the agent is to maximize the reward. Now this RT that I just described, right? So that is called immediate reward, right? So the reward that the agent get right after taking the action by the environment, okay? In reinforcement learning, people care a lot about total reward, right? So what is total reward? It's basically not just the reward that the agent gets right now, but what will be the future state and what will be the potential future reward after that, right? So the total reward is basically sum of all the rewards taken across all the steps that agent has taken. Of course, the immediate reward is also important. There is also a notion of a discounted total reward in the reinforcement learning. So it goes something like this. The immediate reward is R0. We get the reward for the current action. But the future rewards, the R1 and R2 and so on and so forth, they are basically discounted by this gamma factor. Gamma is between 0 and 1. These rewards are discounted, right? So they matter, but they don't matter as much as the immediate reward. So that's the idea behind the discounted total reward. So that's all the RL basics that I need. Now let's talk about previous work in RL for MIP branching. Thanks to Paul for helping me find all this paper for literature review and everything. These are all the works that are done for MIP branching and that basically uses reinforcement learning. These are very nice work and they have very nice results. Let's talk a little bit about this work. So I'm not going to go in detail of each and every one of them, but rather let's talk some general things about this. First one is that all of this work require offline training. There is an agent, which is basically the MIP solver. When we talk about reinforcement learning for branching, the actions for that agent are basically picking a branching variable. Of all the candidate set that we have, the agent or the MIP solver basically has to pick a branching variable, and that's the job of this agent. In order to perform well, they require some offline training. They basically solve the same instance multiple times in order to train their agent. And all of these approaches, they work on specific types of MIPs on which their agents have been trained on. They can basically vary in scales sometimes, but typically they don't work in generic MIPs. They don't work well in MIPLib or those kind of benchmarks. If they are trained for set covering problems, then they basically work well on set covering or something similar type of problems, but in general, not the general MIPS. So that's the idea. Those are some limitations, but apart from these two limitations, they have some really good results. They in fact even beat the current state-of-the-art branching rule that we have in most of the MIP solver, which is basically either reliability branching or hybrid branching. That's kind of a very motivating thing to continue making efforts in using reinforcement learning for MIP branching at least. That's for the previous work in RL for MIP. Now let's talk about the main idea of my project, which is discounted pseudocost. We want to use reinforcement learning for MIP, and when we want to use reinforcement learning for anything, the goal is to basically design a reward function, right? So the agent will, of course, like there is the training process is there, and a lot of other things are there, but one of the main challenge is to design a good reward function. One of the reward function for training an agent for branching is to just give -1 as a reward. Every time the agent branches, we give the reward as -1. It doesn't matter what variable the agent picks, we just give them -1 as the reward. The idea is that if the agent is trying to optimize the total reward or discounted total reward, then it will figure it out that it needs to finish the search in as few nodes as possible. That's the idea behind giving -1 as the reward. In general, it can be made to work, like some of the previous approaches that I described, the previous papers basically that I showed in this presentation. Some of them basically also work with this kind of reward. And so that's like one type of reward function. There is another type of reward function which basically cares a little bit about giving more information to the agent, right? So for example, we can also give bound improvement as a reward. Once the agent branches, we can see how much the LP relaxation bound changed or any other bound change. And then that improvement is the reward. And you might have guessed it correctly. We are actually already doing it by using pseudocost. So pseudocost is precisely that. Pseudocost is that every time we branch on a variable, we keep the record of how much the bound was improved, and we basically take the averages of all those bound improvements and keep it in our pseudocost for that particular variable. So this is an immediate reward, right? So when a variable branches, we record the bound improvement and record it in their pseudocost, but we don't keep track of what happens after that, right? So what happens in the future. That's the idea, right? I want to extend this idea to total reward setting or discounted total reward setting. And that's why I called it discounted pseudocost. Let's see how that works in practice, right? So let's say we are at this node X. For that, we have the LP relaxation LX. Let's say we branch on some variable and we reach to this node Y on one of the branch and we get the LP relaxation LY. Now let's also assume that the variable that we branched on is also named X. I kind of ran out of good names for variables and nodes and everything. So let's say the variable was also X that we branched on. So in that case, what we do is we basically update the pseudocost of the variable X by this Ly minus Lx by dx. So that's one data point that we have added to the pseudocost for this variable X, and eventually we basically take the averages of this kind of updates, and that's our pseudocost for variable X. Okay. So that's what we have been doing till now. But let's say what happens after this, right? So let's say Y is not a terminal node, right? So we have to still branch on node Y. And let's say we branch on node Y and we reach to node Z with LP relaxation LZ. Okay. So in this point of time, whatever variable that we branched on at node Y, we'll update that variable pseudocost, but we don't give any credit to the variable that we branched at node X. That's the problem. So that's what I want to fix with the discounted pseudocost idea. My idea is that whatever improvement we got from Y to Z, part of the credit should also be given to the variable that we branch at node X, because otherwise we would not have been at this state Y. In the same idea, like if we extend it, then we will also want to give this update Lz minus Ly by how much we moved X, that much update for X, right? So, and of course, like these two updates, these two types of updates should be kept separately. So first one is called level 0 updates and second one is called the level 1 update, and both of these averages are separately maintained. Okay, so the level 0 cost corresponds to this R0 in the equation below, and the level 1 will correspond to R1. And if we branch further, then we can have more updates like level 2 and level 3, which will correspond to R2, R3, and so on and so forth. For the first implementation, I focused on just staying at level 1 and not caring about what happens after level 1. But we can, of course, like the idea is that eventually we want to extend it to further levels. So that's the idea of discounted pseudocost. And before we jump into evaluating it, let's also take some points into account. First is that we can actually think of this idea, discounted pseudocost, as an approximation for look-ahead branching. Pseudocost can be thought of as an approximation for strong branching, and the similar fashion, if we extend that idea, then this entire discounted pseudocost, if the gamma is equal to 1, then it is some way approximation of this look-ahead branching. And of course, like strong branching is powerful, but it's expensive. I mean, it results in smaller trees, but it takes a lot of time. Same way, look-ahead branching was shown to be even more powerful than strong branching. It is way more expensive, so we don't use it in practice, but of course, like we can always use its approximation. That's one thing to note about it. The second thing is that the current state of the art is not really pseudocost. The current state of the art is either hybrid branching or reliability branching. In hybrid branching, of course, like reliability branching is also a part of the equation. We actually have to extend this to the reliability branching, right? And there are some problems. So one of the problem is that, let me describe it, right? So for example, we have our discounted pseudocost is like this. We have level 0 pseudocost plus gamma times level 1 pseudocost. Both of those things make up for the entire discounted pseudocost. In reliability branching, all we care about this part being reliable, right? So if we don't have enough number of data points, then we say that, this level 0 pseudocost is not reliable, and therefore we should not be using that unreliable pseudocost, and instead we should do a strong branching on that variable and compare that strong branching results with the other candidate. Now that we are doing discounted pseudocost with two levels, then we have two levels of unreliability, right? So we can have level 0 pseudocost being unreliable, or we can also have level 1 pseudocost being unreliable. Basically not having enough number of data points for level 1 pseudocost for that given variable. Okay. In that case, of course, the logical way of handling this problem is basically to go back and say that, for this variable, one of these two things are not reliable. Therefore, we should do a look ahead branching, and that would be like too expensive. So I said, like, let's not dive into that too much because it will be too expensive. So let's say if one of these two fields are not expensive, then I'll just say that let's not use discounted pseudocost at all for that node, and let's go back to the reliability branching, the default one, right? So it's a kind of hacky way of doing things, but as of now, that's the current state. So it's basically like giving up and switching back to the older metric. So there are issues with that. One of the issues is that at the beginning of the search tree, like where the branching really matters, I'll be switching to reliability branching a lot more, and therefore very few instances are actually affected. That you'll be seeing in the evaluation part when we talk about it. So that's an issue, but I'm open to other fixes that people have to suggest. So we'll see if I can find better fixes than that. For this current idea, let's see how it works in practice. So we did some evaluation, and we'll start with the comparison with pseudocost branching. I did a lot of different types of comparisons. In some of them, I kept pre-solving off. Some of them I kept cuts off. Basically, I turned off pretty much everything that is not related to branching, heuristics off, and all sorts of experiments. Sometimes even I would provide the best known solution. But the one result that really matters the most is this one, which is everything is by default on except for the branching rule, which is switched to the pseudocost branching rule in skip. And this is the benchmarks that are done on MILP dataset for 2-hour time limit and 3 different states. There are total 720 instance seed pairs, and we have comparison of PS cost and DPS cost, which is discounted pseudocost. The time is the geometric means of time shifted by 1 second, and geometric means of node shifted by 1 second. The DPS column shows the ratio for the same metrics instead of the actual time or actual nodes. Obviously, there is not much impact except for the last row, which is the instances that take over 1,000 seconds to solve, which is harder instances. In that case, I see some benefits for time, but it's not a big benefit, I would say. It's still within the noise margin overall. That's some result, right? So at least the noise is in our favor, right? So that's still like good results. And for the other experiments where I turn things off and just compare the branching rules, even in those cases, I was basically getting the similar numbers. That's the comparison with the pseudocost branching rule, which we don't use in practice. The other comparison that really matters more is this one, which is comparison for reliability branching or reliable pseudocost branching rule. This is the comparison where everything is by default on. So it's the skip's default setting versus skip default setting, but the branching rule changed to discounted reliable pseudocost instead of the regular reliable pseudocost or the regular hybrid branching, whatever it is. Here also I see the similar number. The last bracket is the only one that is basically seeing some improvements. Here the time limit was just 1 hour. And you can notice that the number of affected instances are a lot less compared to the previous table. That's because I switched back to reliability branching when either of these two levels pseudocost are not reliable. So that's for the comparison with the reliability branching. And skip also happens to be an MINLP solver. So I had to do a comparison on the MINLP dataset as well. 3 seats of course, and so these are the results for that. Any gains or losses here is basically totally unintentional. I don't expect any gains or losses, and you can see pretty much there is no big difference in there, except for in here the PDI metric is slightly improved. In fact, the PDI metric was slightly improved even in the previous two comparisons as well. There was actually significant improvements in PDI metrics, but when I left Berlin, they told me that there are some bugs in the way they record PDI metric, and so they are trying to fix it. Once it is fixed, let's hope that PDI gains are still noticeable and significant. And if that is not the case, then we'll have to do some more work. If that is the case, but we still see better gains in PDI at least, then my code will be turned on by default. At this point of time, it is already merged in the skip code, but it is by default turned off. And so we'll need basically some more evidence or some more numbers which can confirm that this is actually helpful and not just the noise. So we are basically just waiting for that. Noise or not, or whether whatever it is, right now it is in our favor. So that's the current result. And now let's talk about the future work. There are a lot of things that we can work on to extend this idea and get even better result. So one of the ideas is that pseudocost is first of all not just used in branching, but it's also used in other heuristics. For example, there are a couple of diving heuristics where pseudocost is being used. So we can try and substitute discounted pseudocost there and see how that works. So that's the one future work. The other idea basically came from a discussion with Timo. That idea was that in the hybrid branching, there are a lot of other scores that we keep. There are a lot of other fields that we maintain in skip variable history. And some of those variables, fields or scores can also be discounted. Right? The same idea of reinforcement learning of discounting pseudocost, the way we discounted pseudocost, we can also discount a lot of other scores as well. And that is something that is worth trying. I haven't tried it yet. The natural idea of going for 2 or higher levels of pseudocost is kind of, I'm kind of putting a question mark on here, because at this point of time we would need more signals to know that at least 1 level discounted pseudocost are working well. After that only we can try to extend it to 2 level or more. And the final one again came from Timo is that recall the previous graph that I showed you, right? So we have node X and node Y. When we gave the second level 1 update for variable X, right? At that point of time, the branching was done on this variable Y or node Y, right? Whatever it was. And the idea was that Timo says that it basically, we should only do that if this variable that we branch second is close to the variable that we branch first. And what do I mean by close? It's basically any metric of closeness, right? So how closely those two variables are actually related. If they're not closely related, then the second level of update should be skipped for that variable X. And one of the way of measuring closeness is variable constraint per graph. If variable X and Y are very close, then we can give it. Otherwise, we can not give it, or we can give partial credit to X, not the complete level 1 update, but some weighted level 1 update to X and something like that. So that's the idea. Again, like I haven't found time to work on that. That's, I think, pretty much all that I actually wanted to discuss, right? So in conclusion, basically we worked on this nice project, and we found a way to integrate reinforcement learning concept. And in this way, it doesn't really require any offline training. It basically modifications to the MIP solver, and once you turn it on, then it is already acting. So no offline training is required, and it works on generic dataset. So we showed the results on MIPLib instead of a specific type of MIP. So those are like some nice things to have. Of course, the results are not as good as the other RL works, but they're still something. And I have written a small report on and put it in archive. So if you want to read about it, then you can scan this QR code, and I'll also put the link in the description. Yeah, so it's not properly in a paper format or something. It's just something that I have written so that other people, if they want to read about this work or follow up on this work, then they can basically go and find this work, right? So that's pretty much all for this talk. Thank you.